In this lab, we'll be discussing reaction rates. Reaction rates are how fast or slow a reaction is. Reaction rates can be very slow or very fast. The reaction rate depends on the conditions of the reaction, such as temperature and concentration. The reaction rate can be measured through the disappearance of reactants or the appearance of products. A hypothetical reaction, like the one shown here, can be used as a general expression for reaction rates, because if the reaction rate is known, then the rate constant can be found and the order of the reaction can then be found. In the equation, K concentration A raised to the A concentration of B raised to the B, the lowercase a and b show the order of the reaction. These exponents dictate how much the reaction rate will change if the concentration of A and B, which are the reactants, are also changed.
So the whole point of this lab is to figure out how to measure the rate of reaction of certain reactions. So the whole idea is that we'll use a reaction that is relatively easy to measure its rate of reaction using lab equipment. In this case, we'll be using a spectrophotometer. And in this lab, we'll be using the reaction, which is the decomposition of peroxydisulfate in the presence of iodine. And this measurement is possible because one of the products in this reaction, diatomic iodine, reacts with excess monoatomic iodine to produce triiodide. And we'll be measuring the rate of appearance of the triiodide to find our reaction rate. And the idea behind this is that the rate of reaction is equal to the rate of appearance of the diatomic iodine, which is equal to the rate of appearance of the triiodide. And this formation of triiodide is actually what is being measured and ends up being used as our measure of rate to find the reaction rate of the decomposition of peroxydisulfate.
This experiment employs the use of a spectrophotometer to monitor the decomposition of peroxydisulfate. The presence and concentration of the colored species triiodide is a rate-determining factor of this reaction. The spectrophotometer reads the output of white light that has not been absorbed by the sample and interprets the data to determine the progress of the reaction taking place. Beer's law is the equation that you can see to the right of the slide, and it is how we will determine the concentration of the products during reaction progress. Beer's law relates the measured absorbance of light to the desired value, the concentration. The key to our analysis is that the concentration of triiodide will equal the concentration of iodine formed, with triiodide being our indicator and iodine being our reaction product.
In this experiment, different combinations of volumes of the solutions will be ran in a spectrophotometer to determine the rate law of the decomposition of peroxydisulfate. First, you must obtain the stock solutions, which are potassium iodide, potassium nitrate, ammonium persulfate, and EDTA. Next, you will prepare solution A, which contains both potassium iodide and potassium nitrate, and you can find the volumes of these according to the experiment number from the chart provided, and add these into a cuvette. Next, add 1 milliliter of deionized water and 10 microliters of 0.1 molar EDTA to the cuvette and mix well. Next, place the cuvette into the sample chamber. Then you will configure and blink the spectrophotometer. Next, prepare solution B, which contains ammonium persulfate, and you can find the volume of this according to the experiment number from the chart provided. Add it to the cuvette, mix well, and immediately start acquiring data. Next, you will record the data from the spectrophotometer every 15 seconds for 1 minute total. After you finish these steps, you will repeat them for every experiment shown on table 1 and 2.